just start recording. And like I said, there's so many permutations that I can't do every one, but I thought I'd do one you might see on the midterm. All right. So they get a bit involved. So we're going to do the magnitude and the phase. And so we have h of s equals a times b divided by s plus a times s plus b. And let's set the frequencies to 2 and 2K. All right. Now, on the MyOpen Math, you can't change the axis. It's all in powers of 10. But now I know that I have something that's 2, right? So I'm just going to kind of rescale things and say this is going to be 2, 20, 2K, 20K, 0.2. All right. That way I'm not trying to figure out exactly where to place the number 2. So let's just say we have 2 times 2K s plus 2.
Professor, you're missing
Yeah.
200.
Yeah, I'm missing 200. Thanks. Okay. So, when I look at this, I can kind of rapidly know what kind of shape it is just by looking at S. And if I say, I'm not even going to bother with S equals j omega. If I set S equal to 0, right, I'm going to get, this will drop out, that'll drop out. I'll get 2 times 2K, which when divided into 2 times 2K would equal 1, right, or 0 dB. And then when I make S infinity, this whole thing goes to 0. So in my mind, I was thinking some kind of low pass, right? So I should see something like this in the magnitude. But I know that there's 2 distinct roots, poles. And so I know I should see something like that. Right. And even before I start figuring things out, right, I know that something's happening here and something's happening here. So I'm just going to put a dot at 2 and then out at 2K. So I know that in magnitude, something's going on, right? Now, because this is logarithmic, I can't actually, if S equals j omega, I can't set omega equal to 0, but I can make it small. And the way I do that is I look at the smallest pole of 2 and say, what if omega was a lot less than 2? What would that look like? All right, well, let's 2 times 2K. If omega, actually, I'm going to do it out. So if omega is a lot less than 2, it's a lot less than 2k, right? And it drops out. And I'm left with 2 times 2k divided by 2 times 2k, which is 1. 20 log of 1 is 0 dB. So I start off here, right? And I know that with the asymptotic plot, it's just going to stay there at whatever value you calculate until you get to the pole. All right. Now I'm just going to scroll this up a smidgen. Well, what if omega is between these two roots? Oops, 2k. All right. Poles, excuse me, between those two poles. Oops. You know what? I'm going to do it without a gain of 10, and then we can add that gain of 10 back in. All right. Very easily. And so we'll get 2 for the price of 1. So now if omega, and it's in between, but the approximation is like it's a lot bigger than that and it's a lot less than that. All right. So in this case, if we're in between, well, this is bigger than 2, so the 2 drops out, but this is still smaller than 2k, so that drops out. And so we get j omega times 2k. So I'm just going to, which is 2 divided by j omega. All right. So this is a downward sloping function, minus 20 dB per decade, and it equals 0 dB when omega equals 2. Well, we're already right there. All right. And so now I just have to draw, that's a decade down 20, decade down 20. And now this is more of an estimate. Okay. And now I'm just going to scroll up just a little bit more. What if omega is much, much bigger than the 2k? All right, so 2 times 2k, j omega plus 2. Well, now this is bigger than the 2, so the 2 drops out. This is bigger than 2k, so that drops out. And we get 2 times 2k j omega times j omega. And so this is going to have a minus 40 dB per decade slope. And where's our 2K? All right. And so then the complete magnitude would be this. All right. Now, yeah, you might say, well, find the 0 dB point and draw down at minus 40 dB per decade. But really, the plot coming this way and the plot coming that way intersect. So you might as well just start here and start drawing down 40 dB. And really, oops. The key things are to make sure if you're doing a hand plot, make sure we have 0 dB. Make sure we have the 2 labeled properly. Make sure we have the 2K labeled properly. And then you would just put minus 20 dB per decade, minus 40 dB per decade. I'm trying to draw it as best I can on a grid, but really, like an impressionist painting, you know, they're trying to kind of get to the truth. What is the thing of the thing? What is the definition of the thing through a minimal painting? And really, the asymptotic Bode plot, you know, straight line at 0 dB up till 2. Downward line minus 20 dB per decade until 2K, and then we continue that way. That's really all you need. Now, yeah, in my open math, you have to draw it, and I have the error percentage error high, so it'll mark it correct even if you're making slight mistakes. And be aware, sometimes if you don't enter anything at all, it'll give you points, which I can't fix that. All right. Now, the question was, what about the 10?
Professor,
Yes.
how did you get minus 40 dB per decade?
You know, I'm going to have to come back to that because I have that in a summary chart from last time. And I have to hit a lot of things today. But if I have time, I'll come back to it, or email me right now and I'll get back to you. Okay.
Okay.
I try not to do that, but today I looked at the homework and everything, and I have to keep going. All right. Sorry about that. So back to the 10. All right, I forgot the 10. All right, well, so let's add it back in or multiply it back in. With something darker. So I have 10 times 10 times 10. So where will this be 0 dB, right? It'll be 0 dB at 20. Oh, okay. So if I come back here, that's where it'll have to be 0 dB, but it's still in parallel with this line here. And and I apologize, I didn't do the less than 2. So if omega is less than 2, I multiply it by 10, and the 2 times 2k cancels out. I'm left with 10, and that's 20 dB, right? Oop, nope, sorry. Right, so it's 20, there's the root, and now I'm in parallel, right? And in fact, but the breakpoint is the same, and it would just shift that curve up everything by 20 dB. All right. Now, I'm going to have to redo some of this. So now look at the phase. Excuse me. And so looking at this, that's all real. All right. So if the phase is equal to the phase of the numerator minus the phase of the denominator, that's always 0 degrees. All right. So in this example, I only have to worry about the denominator. So j omega plus 2. J omega plus 2k. Well, both of these drop out, right? I'm left with something real times something real, right? So it's 0 minus 0 equals 0 degrees of phase. And let's see. Gonna put 2. So it's going to be zero phase up until 2 divided by 10. And that's actually something you just have to have memorized. All right. Then we have omega equals to 2. So now I'm just, NS is always going to be real. So I'm just going to stop drawing it for right now anyway. J omega plus 2. J omega. Now this drops out. This drops out. And so I have something imaginary times something real. And that's going to be 2k omega phase $90. Okay. So let's say and I'm going to be using this, the phase equals the phase of the denominator minus the phase of the numerator minus the phase of the denominator, right? Because this is phase 0, this is phase of 90. We don't really care about the magnitude, so it turns into minus 90. And I'm going to have to even scale this, call that 90. All right, so it's going to be 90 right there. Okay. Gonna have to scroll a little bit. Now we have omega in between 2 and 2k. All right, so that's just, again, gonna be our real part. Wait. Hold on a second. That wasn't right. This is much smaller than that, so the magnitude is mostly on the real side. But here, right, you get square root of 2 in a phase of 45. All right, which then when you subtract it, is minus 45. All right. Now, when we do omega between 2 and 2k, that's where this is bigger than this. This drops out. This is still smaller than that. That drops out. That turns into something with a phase of 90, which then you get minus 90. But what you do is 2 times 10, all right? And it stays 90. All right. Now, what happens when omega equals 2k? All right. If this is 2k, it's a lot bigger. It's going to be all j, if you will. So it's going to be minus 90. And again, right now, I also have to do is keep track of the phase. Here, it's actually equal to 2k. Again, I don't care about the magnitude, but when the real and imaginary are equal to each other, it's 45. Okay. So at 2k, it's going to be minus 135. But how do you connect it? Well, this root is now 2k divided by 10. And you just draw a line through it. And really, at that point, you don't even have to work it out, as you know that at 20k or 10 times 2k, it's going to flatten out. And it's going to be minus 180. I'm just going to do that down here, though. So omega greater than 2K. So this is bigger than that. So I have J omega. This is bigger than that. And I have J omega. Now, you might, and this is a tricky thing, you might say, well, that's minus omega squared, which is omega with a phase of minus 180. But that's not how the algorithms work. And you have to match the algorithm. So don't do that. You keep it, the way I found it is to match the algorithm is this would be omega 90 times omega 90. Then it equals omega squared 180. Then you have 0 minus 180. And so it's equal to minus 180. So really don't put it into polar before any multiplication operation. All right. And this holds true with the high pass filter as well. All right. So you just keep it in polar and then do the multiplication. Don't multiply in Cartesian, I guess is what you would say. And so that's pretty much it. Now, what can happen though is, notice these are very separated. If they get close, right, you might not see, you see how you have this flat region in the phase. If they get close, that transition region is going to change, right? It's going to get smaller. And if they're equal, right? In fact, instead of going from 0 to 90 from here, right, it'll go from 0 to 180 and then flatten out. All right. So on the midterm, you'll have A equals B. I think A equals 10 times B, or maybe 100. And then A equals like 1,000 times B. All right. And the phase would change. How that would look in magnitude is if they were equal to each other, there'd be one breakpoint and it would be 40 the whole time. As it gets closer, this breakpoint would just get closer, or it gets or goes the other way. All right. Now I'm going to come back to that one. Because there's other things that I need to talk about. And I know there's a similarly done problem. So here is a Bode plot, but it's in Hertz. Okay. That's how LT Spice does it. The dotted line is the phase and the solid line is the magnitude. And this is frequency. What this is though, is it's input frequency if Vn equaled 1 sine 2 pi f t plus 0 phase. All right. So everything is scaled by 1 because even though it's V out, I know that my input is V out divided by V in. And so this really is V out divided by V in, which is the transfer function. All right. So this Bode plot, right, is S equals J omega. And that means everything is a sine wave, which for all time, because we're going into Fourier analysis. So if this is the Laplace transform, where S equaled some real thing plus J omega, well, now we're saying, what does for all time mean? Oh, minus infinity to plus infinity, f of t, e to the minus, and now there's no real part. Okay. Which means that these input sine waves, right, have always existed. But in reality, as long as you've left it on for a lot longer than 5 tau, that's effectively infinity. All right. So when we just do this kind of hack, S equals J omega, and the sine waves existed forever, we're just using the Fourier transform. So now if Vn equals 1 sine 2 pi 1 hertz time, what's V out? Okay, well, all you have to do is multiply this sine wave by the linear magnitude. So what did I say? 1 hertz. So I look at 1 hertz and the gain is 20 dB. So how do I go back to linear? Well, that's 20 divided by 20. All right. And then how do I deal with the phase? Well, I look and this dotted line, it's very close to 0. Okay.
Wait, Professor David,
Yeah.
what was the sign with the 10 to the power of 2020? Like,
Well, right. So if
like no, the V out equation you had earlier.
so if you have 20 log to the base 10 of V out V in, right, then which is the kind of the gain, right? Well, this is what I need. I can't just multiply it in dB. So then V out equals V in 10 and this equal to 20, right? It'd be 20 divided by the 20. And that gives me my scale factor. Okay. It's just going backwards. Okay. Hello? Okay. And then the phase is 0. Now, what if we picked a point here? Well, the magnitude is 10 dB at I'm just going to call that 600 hertz. So V out 600 hertz is going to equal V in, which was 1, scaled now 4 divided by 20 times the original sine wave, 600 hertz though. But now the phase is minus 64, which you can't do on a graphing calculator because this is in radians, right? And that's in degrees, and you would have to convert it. However, if you're just plotting by hand, right? Draw one period, okay? And call that, 1 over 600 hertz, right? And this is 0, 180, 360, and that's 90, so 60. So I just know that this waveform is going to be shifted or delayed by 64 degrees. So it's going to start at 0 around here. All right. And .58. So the gain is 1.58. So if this is 1, right, 1.58 would be kind of up here. And now this is, I do struggle with trying to draw delayed sine waves. All right. So the gain is bigger than 1 and it's shifted. All right. If you were to plot that out, you'd have to change that into radians, right? Now, I'm going to pick another point. I'm just going to try to extend this a little bit. So at this point, I'm going to call that 3 kilohertz. Okay. I can tell that the phase is minus 90 and the gain is minus 2 dB. So V out will equal V in, right, which was 1 volt, 10 to the minus 2, 20 sine pi 3K T minus 90 degrees. So we'll call that 0.8. So I've been delayed. I've moved that peak over 90 degrees. Now, this all looks like I can draw all of these on top of each other, right? But it's actually, let me see if I can find a better spot. This is why the Bode plot or the frequency domain is so useful, because let's just say, let's just try to draw a sine 2 pi t, sine 2 pi 10t, and sine 2 pi 100t. All right. I'm just going to call this 0 to 1 second. Great. It's a little bit sloppy, but you know it's a sine wave. Now this one is 10 times faster. So 1, 2, 3, 4, 5, 6. So that's 2, 4. So now this is really messy, even at 10, right? I'm trying to, of course, the amplitudes are changing in my drawing, but imagine they're all the same, right? I'm trying to fit 10 of those in there. Now, I'm trying to fit, you know, it looks kind of like I'm just coloring in a coloring book, not very nicely, right? You just can't see it, right? It's impossible. And then only that, then to see that this is delayed by a certain amount of phase, you measure it this way if you're doing it like that. But really, the time domain makes it really hard to see different frequencies. Also, what if the gain is 20 dB, right? That's times 10. So what if this signal is 10, but then at the higher frequency, it's 2? Well, then it's only coming up to here. And then what at the other higher frequency, it's 1. Then it's only coming up to here. You can barely see it. But in the Bode plot, it's very easy to see because we're looking at a logarithmic of the gain at any given frequency, and the frequencies are stepped logarithmically, right? So now I can, you know, rapidly point to various spots wildly changing in frequency and really talk about the system. All right. Now, I try not to show things done incorrectly, but sometimes determining, you know, is this right or wrong? You know, that's a good skill to have, right? Because if you check your own work and you know what makes it right and what you need to make it right, well, then you can check your work. So I have a Bode plot here. It's a high pass, right? Because if S equals 0, this whole thing goes to 0. And if it equals infinity, it goes to 1, right? So before I do anything, right, I can know what kind of shape, right? I'm going to have this kind of shape with one breakpoint because there's, you know, one breakpoint here and an order of 1 here. All right. So I already know that's what it's going to look like. Okay. And because I know that shape, right? I know, that's going to be 0 dB, and that's going to be at 2K. And that, yeah, the phase is going to go from 90 down to 0. Again, this is done, how to do a high pass filter is done in the notes. All right. So what makes a good Bode plot of this? Well, what do I need to see? Well, here's the magnitude. In this particular example, it's 0 dB AC gain. It's a first order, so it's 20 dB. And then there's my 2K. And then I know that the phase will be 90 up to 2K divided by 10. It'll be 45 at 2K, and then it'll be 0 greater than 20K, right? That 10th and 10 times, right? This kind of thing, All right, so what would make a bad Bode plot? Well, this should be relatively straightforward. It's a great Bode plot. It has magnitude and phase. It has 0 dB. It has the right checkpoints. All right. Maybe I didn't have the right checkpoints here, but I can easily add those back in. It's just this is a low pass filter. All right. So it's just the wrong shape, the wrong direction altogether. All right. Here, okay, 0 dB, right breakpoint. Oh, high pass magnitude shape. But look at the phase. Oh, it's at 90. Okay, it starts going down at 1/10 of 2K, great. And then it stops, right? This isn't there. So it's wrong. You got to have, because then it just looks like a low pass filter shape. You've got to have it flat, down, flat in the right spot. Okay. And then D, that's not good because the phase is missing. Right. So let's just take the, let's look at the transfer function where S equals J omega. All right, so we have S, J omega, divided by J omega plus 2K, I believe. Well, these are in Cartesian coordinates, right? And I have a real part, and I have an imaginary part, and I have a real part, right? Well, that's two pieces of information, right? Because I'm on, I have this pole here and a 0 here, right? Where I've got real and imaginary, complex data, real and imaginary. If I only have magnitude, I've lost half the information. All right. And so you need magnitude and phase, right? To have a correct Bode plot, you need both, and both need to be done. All right. Now this is kind of review by now. All right. In that I've derived these several different ways, but now I'm going to try to tie it together a little bit. All right. So this is an RC circuit, and it's in the time domain because you can see the step, right? How do I solve it? Well, I solve it with time domain differential equations in calculus. Here's the S domain. I'm using the impedance, and I've taken the Laplace of a step. All right. Now, again, I'm not going to derive it, but the impulse response is 1 over RC, this decaying exponential times UT, or omega naught. We can use omega naught there. Here, I can use voltage division, and I come up with this equation, right? And you can see how RC and omega naught are equivalent. All right. Now, this is the plot of the impulse response. The peak is 1 over RC, and it takes 5 RCs to decay to 0, or 5 divided by omega naughts. Right. So the bigger omega naught, the smaller, the higher this gets, and the thinner the base gets. Here, right, on the magnitude, I'm at omega naught. If omega naught gets bigger, it goes this way. Omega naught gets smaller, it goes that way. All right. And here's the step response. So here, let's call this omega 1. We'll call that omega 3, omega 2, and omega 1. All right. So the larger omega, the faster it reaches that step. Okay. The smaller omega, the slower it goes. So what would this look like on the Bode plot? That would be like omega 1, omega 2, and omega 3. And if you think about, right, this is a Bode plot. Omega 3 is getting rid of all the sine waves over here. Omega 2 is letting in more sine waves, and omega 1 is letting in many more sine waves. And the more sine wave frequencies you let in, the sharper this gets. And if I took omega to infinity, well, I would get the original step function out. Okay. So here we have the high pass. Here's the time domain. Right, here's the frequency domain. And we're not going to talk too much about the phase. All right. But here, right, I have the delta function, and then I have that decaying minus that decaying exponential. All right. And the step response is just that's just that function. So in this case, remember, this is 5 divided by omega 3. Okay. So this is omega 3 is smaller than omega 2 is smaller than omega 1. Yep, there's notes. There's notes for everything, guys. Okay. So omega 3, right, is smaller. So it's going to be here, right? And that's the high path shape. Then blue is going to have a higher omega naught than that. Okay. And then this is going to have a higher omega naught than even that. And what it is omega 3 is blocking less low frequencies, right? Which is why it takes longer to decay, right? Omega 2 is blocking, a little less than, less low frequencies. So it's a little sharper. And this is only allowing high frequencies. So only that gets in. Okay. And so this is the step response, which we call that the step. That's an edge. So if I put in this into the system, this detects the edge and then decays to 0, right? So it's kind of detecting a slope. And the higher this is, the more accurately it can just detect slope. All right. Back here, it's passing DC, right? So eventually it goes to a DC value. But the more higher frequencies I let through, the sharper it gets. Okay. So we should be able to kind of do an eyeball convolution, all right, of this. All right. So here's a shape. That's the mathematical description. And it's 1, 2, 3, 4, 5, 6. All right. And now here is the impulse response of a low pass filter. And here's its Bode plot, right? Well, this shape starts and ends at 0 and takes 6 seconds to do that. This starts and ends at 0. And I'm calling this distance 3 seconds. So it's going to be 6. That shape is going to be non-zero, right, for that amount of time. And if the step response of a low pass filter is this, see how it takes these corners and it rounds them? Well, then, and the longer this is, right, or the more high frequencies that's eliminated, the more it'll be rounded. And so just by eye, right, I'm going to round things like that. Okay, so it just smushes out that shape. All right. And let's call that omega 1. Now, omega 2, it's only 1 second. So I'm going to be here. That's where it's going to end. 5 tau is 1. So omega naught is bigger. It's allowing more AC, more higher frequencies. And so it's going to kind of follow the shape even closer, right? And understand these tips aren't drawn to scale here, all right? And then omega-3, let's give that a nice color. It's very thin. It's letting in a lot of frequencies, right? And so that's 0.1. I'm going to add to the 6th. And now it might look to the unaided eye practically the same shape. All right. High pass might be a little bit harder to understand, but really it's so if I'm going to convolve these shapes, right, omega-1 in this case is letting in a lot of frequencies closer to DC even, right? So it should follow the shape, but it blocks DC, so it might start to decay. Then it follows the shape, and then it follows the shape. Then it'll decay, and then, well, oh, sorry. If that's 5 tau, right, that'll go on for 5 tau. But then something interesting happens here is that it'll act like it'll take the derivative of this. So it'll go up, right? Then it'll go to 0. Then it takes the derivative again, right? But then right here, it goes, the derivative goes negative, then it goes back to 0. And does this. So this went, and actually, yeah, it goes down -1. So +1, -1. This should be -1. So, but that's blocking all DC. Now, I didn't tell you what the, anyway, that's what that would look like. So if it looks like it's taking the derivative of the slope, derivative, and you're seeing, oh, that's a that's a constant slope. That's 0 slope. It won't detect 0, just would decay to 0, right? The derivative of a straight line is 0, so it goes back to 0. All right. Now, this was giving me a difficulty. So I'm just going to cheat it. So here's a low pass filter. I ran out of time to do a triangle, that step triangle. All right. But so the period is 2. All right. And then notice it's taking time to get there. So in fact, 5 tau is longer than this shape. And so it's not even getting to where it's going, right? So I actually have to make it longer for you to see it. Just gonna go for very long. Okay. So if this were to flatten out, then it would go to 0, but the shape is repeating. So here's the thing, this shape is 20 seconds long and 5 tau is 5 seconds, right? So now if I made tau smaller or omega naught higher, it's getting, very close to the shape. And then if I made it even smaller, tau smaller or omega naught smaller, right, you practically can't tell the difference, right? Now, if we simulate the you see our low pass, right? So that slow shape had a cutoff frequency in this range, right? Now, if I match it to the one in between, you'll see omega naught go out, right? And then if you match it again, it keeps going farther and farther, right? And so the more, that's like the more frequencies it collects, right? Now, now we get the high pass, right? And I keep so the breakpoint changes, right? It's just the denominator is changing the function. All right, so what will this look like in the time domain? Okay, so it takes time to turn on, and then you see a slope, right? Then it takes time to adjust, and then the slope goes down. Now, yeah, you know that that's slow. No, actually, Yeah, the slope is 0.1. Right? Because it's taking me 10 seconds to go up 1. All right. So what if I made it faster? Okay. Now it scales it, and I'm going to have to, so it reaches that slope faster, but then it's, because of the time constant, now it's reaching its smaller value, which I can put into an op amp and say, oh, let me multiply that by 10. Right. Oh, now I'm back to the proper slope. Right. And then if I do it again, okay, it's like, let's put it in the, right. So it rapidly takes that derivative, right? It's just scaled to incorrectly, right? So this is taking the derivative, all right? And that's something that this, you will often be called, that's an integrator, and that's a differentiator, okay? Because this is going up and then flattens out, and this is going down. And so in this region, right, we have something divided by S, right? This is a Bode plot. In this region, we have something times S. So here it's acting like a ideal integrator. Here it's acting like an ideal differentiator. And so sometimes you'll see that, right? But you can have a circuit where this is 1 over RCS, right? And that's an integrator, right? So what that would be is 1 over RC. Of course, you'd have to switch things. And if you had this, it would turn it into a differentiator. All right. And if I didn't want this, right, I could put it in to another inverting gain stage. So I know people have to go. So if the person who had that question around here, and I forget what it was, you can stay and ask me right now. Okay, but that
Okay.
I'm going to stop